We are going to continue our discussions on closed chain parallel manipulators. So, closed chain manipulators. So, to give you the overview of what we are going to discuss in this lecture. So, the displacement analysis of closed chain manipulators, we are going to look at the example of a 3 RPR parallel manipulator which has 3 degree of freedom. We have discussed what a closed chain robot is. It is also known as a parallel manipulator because all the actuators are connected parallelly to the end effector as this figure shows. So, this is one actuator, this is a second actuator, the third actuator, they are all connected parallelly to the end effector. So, this is the end effector and all the actuators are directly connected through links to the end effector. So, this is a parallel manipulator. So, we are going to continue our discussions on closed chain planar robots. Let us look at some of the 3 degree of freedom closed chain planar robots. The first chain I have mentioned is the 3R. So, according to this nomenclature actually it is 3R dash 3R. So, as per our previous nomenclature this should be 3R dash 3R dash 3R. So, written in a compact form as 3 times 3R. So, let us look at this kinematic chain. We have a ground link and the end effector link as I have shown. Now, we have 3R legs. This is one 3R leg. This is the other 3R leg. This is the third 3R leg. Let us calculate the degree of freedom of this. This ground is 1, 2, 3, 4, 5, 6, 7 and the end effector is 8, link 8. So, number of links is 8, number of joints 1, 2, 3 plus 3 6 plus 3 9. So, we have 9 joints, 9 kinematic pairs, each having degree of freedom 1 since they are all revolute pairs. So, therefore, summation of degree of freedom is 9. So, therefore, degree of freedom is 3 times number of links minus 1 minus 3 times number of joints plus summation of degree of freedom of each joint. So, this gives us 3. So, this closed chain planar manipulator has 3 degrees of freedom. Next is the 3 times RPR, which we are going to look at For that also the degree of freedom calculation remains the same, because some of the revolute pairs have been replaced by prismatic pairs. So, 3 revolutes have been replaced by 3 prismatic pairs. So, let us move forward and look at our 3 RPR chain as shown here. We have this end effector link in blue, and there are 3 legs which carry a prismatic, an actuated prismatic pair. So, you can see that the coordinates of the end effector point x e and y e are to be, and the coordinates of the end effector point and the orientation. Since this has 3 degrees of freedom, so we can control 3 things. So, position of the end effector and the orientation of the end effector link, and we have actuations at these 3 prismatic actuators in terms of S2, S4 and S5. So, we know that the displacement analysis problem has 2 parts. One is the forward kinematics problem, in which the actuator inputs are given and we are to find out the output. Output means the end effector position and orientation. In the inverse kinematics problem, for a given output, which means the end effector position and orientation is specified, we have to find out the actuator inputs. So, let us look at the forward kinematics problem for the 3 RPR parallel manipulator. So, here we are given the actuator throws S2, S4, S5. So, we are given the lengths of these actuators or these legs. We have to find out the coordinates of the end effector x e and y e and the orientation of the end effector link. So, this is the forward kinematics problem. So, let us begin with writing out the coordinates of the points on the end effector link. So, here I have written out the relations between the coordinates of point A and the actuator throws S5 and S2. So, you can very easily derive these expressions. So, this is the origin of our coordinate system. So, x a square, so x coordinate of a square plus y coordinate of a square is the length of actuator to S2 square. So, it is length square. The length R A square, which is S5 square, is given by x a square plus y a minus L1 whole square. So, essentially these are equations of circles. So, the first equation is a circle about the origin with radius S2. The second equation is the equation of a circle with radius S5 and center 0 L1. So, R, essentially the point R. So, therefore, if I subtract the second equation from the first, then x a cancels off. What I arrive at is this, which can be written as y a plus y a minus L 1 into y a minus y a minus L 1 is S 2 square minus S 5 square. So, that gives us 2 times y a minus L 1 times L 1 is equal to S 2 square minus S 5 square. So, from here I can solve for y a. So, 1/2 of so, this is the solution for y a. So, I have found the y coordinate of point A, then finding out x coordinate of point A is trivial because I have this equation, this is the first equation. So, I can solve for x a. So, we have two solutions with plus or minus signs. So, let us look at this formally. So, this was the solution of y a and x a. This has two solutions. So, I have written out these two solutions here. These are the coordinates of point A. So, the two solutions are specified in given in terms of these two signs. Now, I can express x b in terms of coordinates of x a, and I will now introduce this phi. So, x b, so I am expressing the coordinates of point B in terms of coordinates of point A, which is now known to me, plus d times cosine phi. So, this distance a b is d, as you can see, this is d cosine phi, this angle being phi, and this is d sin phi. So, therefore, x b, x coordinate of point B is x coordinate of point A plus d cosine phi, and y b is equal to y a, which is not also known to us, plus d sin phi. So, once I have the coordinates of point B, of course, in terms of this unknown phi, phi is unknown as yet, then I can express the length of S 4, I can express the length S 4 square as x b minus x cube whole square plus y b minus y cube whole square. So, that is S 4 square, that is what I have written here. by substituting the expressions of x b and y b, and also x q, y q is of course 0. In this equation you will find what is not known is phi. Phi is as yet unknown. X a is known, y a is known, and S 4 is given. So, phi is the only quantity that is not known. So, when I open up and simplify this equation, I can express it in this form, which you can very easily do. So, since phi is unknown to us, I express it in terms of sin phi and cosine phi, where a, b and c they are completely known, because y a we have calculated, x a we have calculated, and S 4 is given to us. So, the only thing that is not known is phi, and we know how to solve this equation. We make this substitution, we define x as tan phi by 2, express sin phi and cosine phi in terms of x, substitute back in our equation, get this quadratic in x whose solution is known to us. So, we know tan phi by 2 in terms of a, b, c which are known to us. Once we have phi, we have this expression of tan phi by 2. So, I have written out the expression of tan phi by 2 in terms of a, b, c, and there are two solutions of phi from here, phi 1 and phi 2, which are because of this sign positive, choice of this sign positive or negative here. So, this is with the negative sign and this is with the positive sign. So, these are the two solutions of phi. Here we need to go back once to look at this expression and recall that there were two solutions of x a y a. So, x a y a had two solutions, one with positive sign of x a, the other with the negative sign of x a. So, there were two solutions of x a and y a. Corresponding to these two solutions of x a and y a, you will have two values of a b c. You may call them a 1 b 1 c 1 and a 2 b 2 c 2. So, therefore, for each value of a b c, you will get two solutions of phi. This is what we have looked at. So, for each value of a, b, c, you have two solutions of phi, phi 1 and phi 2. Now, since there are two sets of a, b, c, call them a 1, b 1, c 1 and a 2, b 2, c 2. We will now have four solutions of phi. So, two solutions for this and two solutions for this set. So, there will be 4 solutions. Now, once we have the solutions of phi, we can now express the end effector coordinates x c in terms of x a plus 2 times d cosine phi. Now, this is what is d. So, 2 d cosine phi, this being phi, and this is 2 d sin phi. So, x e will be x a, x coordinate of a plus 2 d cosine phi, and y e similarly will be y coordinate of a plus 2 d sin phi. And remember that we have these solutions of x a and y a. So, finally, we have these 4 solutions which we try to understand graphically. So, we were given S2, S5, S4. So, these were given, we were to find out x e, y e and phi. Now, we think of how we will assemble this mechanism. So, this point A belonging to this link, this leg can move on this circle. So, as we rotate this leg, A will move on this circle. Since S5 is also specified, if we rotate this link, then A will move on another circle given by this. So, this is the circle with radius R A or S5, same as S5. So, wherever you have intersections of these two circles, A can lie. So, A can lie on the intersections of these two circles. So, there are two possibilities. One is this possibility that has been shown, the other is this possibility. So, these are the two solutions of x a. You can see, you can check that y a remains the same, the y coordinate of A remains the same. So, the x coordinate of A has two solutions. So, as an ordered pair, A can have two coordinates, one is here, the other is here. Now, corresponding to this solution, let us say the first solution as shown. Now, since S4 is also given, so the revolute pair B can lie on the intersection of the circle obtained by rotating this leg. So, when you rotate this leg, so B moves on this circle. Now, because A is fixed here, you can rotate the end effector link. So, therefore, B can move on another circle, which is this. So, on the end effector link, B can rotate on this circle. So, therefore, the intersections of these two red circles, which are here and here, are the possible solutions where B can be assembled, and that will fix up the end effector link. So, therefore, x e, y e and phi get fixed. Now, A has this solution, there is a second solution of A. So, therefore, when you choose this solution of A, then this end effector link, when you rotate, so let me draw out these two legs. So, this is the second solution for A, and the end effector link can now be made to rotate about this point A, and the S4 link still rotates. So, B on the S4 link still rotates on this circle. So, there are two intersections of this, as you can see here and here. So, this is one intersection, this is the other intersection. So, this is where B can lie. So, there are two solutions of B for this second location of A. For the first location of A, there were two solutions for B. For the second location of A, there are two locations of B. So, there are 4 solutions. So, these are the 4 solutions that we have. So, let us look at this once again. So, we started off with this circle of radius S2. We want to first locate A. So, we first make a circle with radius S2 about the origin, which is P. Then this second circle with center at R and radius S5. So, there are 2 intersections of these 2 circles. These 2 intersections correspond to the 2 solutions of A. Now, once A is fixed, then we have to locate B. So, the end effector link AE can rotate about A, and hence B describes a circle, and similarly the leg QB of length S4 can rotate about Q as a center with radius S4. So, I have drawn this circle with center at Q and radius S4, and with center A, the end effector link can rotate with radius. So, and rotate about A, the radius is D. So, that is the second red circle. So, the intersections are the correspond to the point B, the intersections correspond to point B. So, there are 2 intersections. So, 2 solutions for B. This is for the first choice of A. For the second choice of A, the center at A shifts to the second solution. So, B can lie on the smaller red circle on the end effector link. So, the intersection of the 2 red circles again correspond to the 2 solutions of B corresponding to the second solution of A. So, these are the 4 solutions. Let us quickly look at the inverse kinematics problem. So, here we are specified x e, y e and phi, which are the position and orientation of the end effector and we have to find out S2, S4, S5 which are the actuator throws, the prismatic actuators. So, here I have written out the coordinates of point A in terms of the known quantities. You see xe is known, phi is known, ye is known. So, all these are known, xe, ye and phi, these are known. So, therefore, I can calculate xa, ya, xb, yb, the coordinates of these 2 points. Now, once I know the coordinates of these 2 points, it is a matter of simple geometry to express S2. You see S2 is this, S2 is nothing but square root of xa square plus ya square. Then S4 is nothing but square root of xb minus L1 whole square plus yb square from simple geometry, and similarly S5 is square root of xa square plus ya minus L1 whole square. So, given xe, ye, phi, so these are given to us, we have been able to calculate the lengths of the actuators S2, S4 and S5. So, this is absolutely straightforward. So, let me summarize. We have looked at the displacement analysis of a closed kinematic chain manipulator, and we have discussed the example of the 3 RPR kinematic chain. We looked at the forward and the inverse kinematics problem for this chain. So, with that I will close this lecture.